Okay, in the last lecture we talked about internal flow, and we focused on the hydrodynamic aspects of internal flow. So the velocity distribution, the momentum boundary layer, and we ended with sort of thinking about the pressure gradient, which is what we really care about, and how the pressure gradient is correlated with the friction factor. And in the next lecture, we'll talk about where to find those correlations. So what I want to do in this lecture is talk about internal flows again, but this time focus on the thermal aspects. So we're going to focus on the temperature distribution, the thermal boundary layer, and then the heat transfer coefficient and the Nusselt number. Okay, so this is sort of where we left off, this picture for an external flow. So this is an external flow. We have a boundary layer that grows. The way it's drawn here, it's laminar on this plate, right? It grows like square root of time, which is square root of x. And in terms of what we care about, which is usually the heat transfer coefficient, where the boundary layer is thin, the heat transfer coefficient is really high because you have to conduct only across a very thin boundary layer. But as that boundary layer gets thicker and thicker, of course, the heat transfer coefficient gets smaller and smaller because you have to conduct the energy farther, right? So we can use this conceptual understanding to think about what happens for an internal flow, right? So for an internal flow, let's see if we can move forward. Same kind of thing happens, except for now what makes an internal flow is that this boundary layer, this laminar boundary layer, can't keep growing forever. It eventually becomes confined or bounded, right, by in this case a boundary layer that's growing from the other side of the duct, right? And so that's sort of the characteristic of an internal flow, is your boundary layers get stuck. Okay, so in this case, when the thermal boundary layer gets stuck, when it's no longer able to grow, you go from this developing region to the fully developed region, right? So when this was a momentum boundary layer, we called this developing region the hydrodynamic entry length, right? And then we called the fully developed region the hydrodynamically fully developed region. Well, here we're talking about a thermal boundary layer, so we're going to call this the thermal entry length, and we'll call this the thermally fully developed region, right? So otherwise, though, the behavior in terms of the heat transfer coefficient is consistent with what we know from an external flow, where the boundary layer is thin. I don't have to conduct energy very far. I get a very high heat transfer coefficient. As the boundary layer grows in this developing region, the heat transfer coefficient drops. Eventually, though, unlike in an external flow, the boundary layer stops growing, right? And so when the boundary layer stops growing, the heat transfer coefficient stops dropping and it becomes constant, right? So the heat transfer coefficient, the local heat transfer coefficient in an internal flow becomes constant in the developing region. And that's just like how the shear stress, the local shear stress in an internal flow becomes constant in the hydrodynamically fully developed region, right? Things stop changing. Those things are governed by the thickness of the boundary layer. When the boundary layer stops changing, those things also stop changing. So we can do the same kind of mental exercise for an internal flow, where we think about what the temperature distribution might look like at various locations. Right? In order to do this, I have to tell you what the boundary condition is in terms of what's going on thermally here at the surface of the duct. So there's all kinds of things that could happen here at the surface of the duct. I could apply a heat flux of some type. In this case, I'm going to assume that the surface of the duct right here at y equals 0, and then also over here at y equals the diameter, at those two locations, the surface of the duct is specified and equal to some constant value, T sub s. So T sub s is the surface temperature. T infinity is the free stream temperature, or the inlet temperature, right? And in this case, Ts is greater than T infinity. So the duct surface is heating up the fluid, right? Again, that's a boundary condition that could change as you have different problems, but that's what we'll do now. So if I am in the developing region, the thermally developing region, what would I have? I would have, obviously, at the surface of the duct at y equals 0, I'd have T sub s, And then if it's a laminar flow, as I move through the boundary layer, I'll get this smooth reduction, this smooth temperature gradient. And then when I get out to the edge of the boundary layer, I get to fluid here in the center of the duct. That's all at T infinity. So this fluid in the center of the duct has no idea anything has happened yet, right? So I do not get the acceleration, the equivalent or the analog of the acceleration that I get for the velocity distribution, right? This fluid thermally has been unaffected by the presence of this duct, right? The velocity out here has increased a little bit. The temperature, though, hasn't changed at all. That's what's happening here. As I move down the duct, so now we could go down here to the point where the boundary layers just join, and what I would expect is that at that point, the thermal wave would just hit the center. So when I get to this point right here, I would expect that the thermal wave just hits the center of the duct, right? So at this point, the fluid that's flowing right at the center, it just begins to understand that something happened at the edge, right? So if we keep moving downstream, so we keep moving down the duct, what's going to continue to happen? Well, when we kept moving down the duct and we kept sketching the velocity distribution, we said, if we keep going and the duct cross-section doesn't change and the properties don't change, the velocity distribution doesn't change, right? But that's not actually true here, because as I keep moving down the duct, at least for this boundary condition here, I'm going to keep putting energy into the flow, right? And the only way that energy the only place it can go is to heat up the flow as it's moving along. So I would expect actually the temperature distribution continues to change, even though the boundary layers are stuck. So if I keep moving down the duct, what happens is that, the temperature at the center now starts to increase, right? If I go far enough down the duct, I'll get to a point where the temperature all the way across the duct is T sub S. I've heated that fluid up all the way to the duct surface temperature, right? This is, if you think about it, exactly equal to a plane wall transient problem, where you at time equals 0, you change the temperature at the surface of the plane wall, and then the midpoint of the wall is adiabatic, right? So for a little while, you have something that looks like a semi-infinite body as the thermal wave is moving through the wall. At some point, the thermal wave hits the center of the wall, right? Of course, the wall doesn't stop heating at that point. At that point, the center of the wall heats up, and eventually the wall comes to some uniform temperature, right? And this is because this is a laminar problem, right? It's basically a conduction problem. Not exactly, but basically. And so that's what the temperature distribution looks like. We need to define for ourselves a reference temperature that makes sense for this situation. And the point to this is that, when we had an external flow, the reference temperature we used was always T infinity. And that made perfect sense, because in an external flow, wherever I was at on the surface, if I sort of just moved away from that surface in the y direction, eventually I would get back to fluid that was at T infinity. But you can see here for an internal flow, that's no longer the case. In the developing region, that is the case, right? In the developing region, if I move far enough out, I'll get back to T infinity. But as soon as I hit the fully developed region, as soon as I get past the thermal entry length, if I'm out here, if I move away from the duct surface, I'm never going to get back to fluid that's at T infinity. And so T infinity as a reference temperature loses its relevance, right? I need a reference temperature that characterizes what is the temperature of the flow at this particular location, right? And that reference temperature is called the bulk temperature. Sometimes you'll see it called the mean temperature. Occasionally you'll see it called the mixing cup temperature. It all means the same thing. It is all the single temperature that you could use in an energy balance, right? It's the single temperature that represents how much energy is being carried by the flow. So if this is my duct and I put a control surface across my duct right here, and I want to know, I'm doing an energy balance, and I want to know what is the energy associated with the flow crossing the surface, I actually have to do an integration, right? If you look back, there's a temperature distribution. I have to integrate over all the differential areas. What is rho times C times U times T times dA, right? That's the energy moving through all these differential areas. I have to integrate it across the entire duct. And that's what I've done here, right? So that's an integration that would require me to know the temperature distribution and the velocity distribution. And this would be the enthalpy flow across this control surface. What is the mean temperature? The mean temperature is the one temperature that I can use in an energy balance. So m dot times c times T sub m is the amount of energy crossing this surface. That's exactly equal to this integration, right? So T sub m is the one temperature you can use in an energy balance. When you would do a thermal problem and somebody would tell you, you have air flowing through a pipe at 35 degrees Celsius. Well, we know now that actually, depending on where you are in the pipe, air doesn't flow through the pipe at a single temperature. It probably has some temperature distribution, right? What is 35 degrees Celsius then? 35 degrees Celsius is the mean temperature of the air. It's the single temperature that I can use in an energy balance to get the right answer. And if you look at this for a second, you'll realize that the mean temperature is not just the average temperature, right? It's actually the velocity weighted average temperature, because the velocity is important in terms of how much energy is crossing the boundary. So if I go back here and think about, what's the mean temperature at this location, it's not just going to be the average temperature. It's actually going to be more closely weighted towards the center temperature, and that's because the velocities in the center are higher, right? So these temperatures here in the center actually matter more than the temperatures out here on the edge where the velocity is lower. So the mean temperature is the velocity weighted average temperature. It is the single temperature that we can use in an energy balance, and it is the appropriate reference temperature to use when we are analyzing an internal flow, right? So when we think about how the mean temperature must be varying for different situations, right? So the mean temperature reflects how much energy the flow is carrying. In this particular situation where I have a constant surface temperature, I come in at T infinity, right? So the mean temperature at the inlet is obviously T infinity because it's a uniform temperature T infinity. As I move through the duct, what's the mean temperature doing? Well, the mean temperature here for this temperature distribution is higher than it was at the inlet. This is even higher. This is even higher. Eventually, the mean temperature is T sub s, right? So the mean temperature for this situation is approaching the surface temperature in something that looks kind of like an exponential, right? The mean temperature is the reference temperature that we will use when we do things like define a heat transfer coefficient. So for an external flow, this was our definition of the heat transfer coefficient. We said the heat transfer coefficient is the heat flux at the surface divided by Ts minus T infinity. So our temperature difference driving that heat flux is Ts minus T infinity. And again, this works because no matter where I am on this surface, if it's an external flow, if I move away from the surface, I get back to T infinity. So this is the appropriate driving temperature difference. For an internal flow, the heat transfer coefficient is defined a little bit differently. It's the heat flux divided by Ts minus Tm. So Tm is the reference temperature, and Ts minus Tm is the temperature difference driving the heat transfer. And again, this makes a lot of sense if you think about it, right? The temperature difference driving the heat transfer here versus here versus here versus here for this situation is going to be lower because the mean temperature is lower, and you can see it. You can see it if you just look at the temperature distribution. The mean temperature associated with this had better be higher than the mean temperature associated with this or associated with this. So this is our definition for the heat transfer coefficient for an internal flow. All right, so let's figure out how long the thermal entry length will be, assuming it's a laminar flow. So this is basically the same exercise we did for the hydrodynamic entry length. We said we sort of know how these boundary layers grow. If they're laminar anyway, they grow by molecular diffusion. So 2 times the square root of alpha times T, where alpha is the molecular thermal diffusivity, right? So, and T is X over U sub M. So here's my very approximate equation for how these boundary layers grow. If I want to know how long it's going to take for the boundary layer to become half the hydraulic diameter, all I got to do then is plug in dH over 2 for this thickness, and that's going to be where I've hit X of FDT lam, so the thermal entry length for laminar flow, and that's all I did here. The rest is a little bit of algebra, right? So I square both sides, and I'm going to solve again for the entry length normalized by the diameter. So I bring one of these diameters to the other side. I bring the rest of this stuff over to here. So I get the entry length to the diameter ratio is, one of these diameters stays, and I have U sub m over alpha, and 4 times 4 is 16. So I'd like to express this in terms of the Reynolds number and the Prandtl number. So right now what I have here is not either the Reynolds number or the Prandtl number, but if I multiply and divide by the kinematic viscosity, then I get the Reynolds number is this group here, and the Prandtl number is this group here, right? So this is then 0.063 times the Reynolds number times the Prandtl number. So the Prandtl number obviously didn't appear in the hydrodynamic entry length equation, but it does appear in the thermal entry length equation, which makes sense because obviously it's going to depend on conductivity. If you remember the hydrodynamic entry length equation, it was just 0.063 times the Reynolds number, whereas the thermal entry length equation is 0.063 times the Reynolds number times the Prandtl number. These two equations look a lot alike, right? In fact, if I divide them, what I find is that the thermal entry length divided by the hydrodynamic entry length is just equal to the Prandtl number, right? So the ratio of these two lengths is related to the Prandtl number, which makes a lot of sense because the ratio of the boundary layer thicknesses was related to the Prandtl number. So, if I think about what this means, in most cases, for most fluids where the molecular Prandtl number is around 1, right, because energy and momentum are being transported using the same mechanisms, I would expect that the entry lengths would be pretty comparable, right? The flow would become fully developed right around where it becomes thermally fully developed, right? If I have a fluid like an engine oil that has a Prandtl number that's much higher than 1, according to this, that says then that the thermal entry length is going to be a lot longer than the momentum entry length. And I think that makes sense because a fluid like an oil is going to be really good at transporting momentum, right? So here, the boundary layer, the momentum boundary layer will grow very quickly, and it'll very quickly become hydrodynamically fully developed, whereas it's not so good at transporting energy, right? So the thermal boundary layer will grow much slower, and as a result, it takes kind of a lot longer in terms of duct length in order for it to become thermally fully developed. And the opposite thing might happen for a fluid like a liquid metal. All that makes sense, I think, based on what we already know about boundary layers. In terms of if you have a turbulent flow, well, we said that if you have a turbulent flow, we can predict when that will happen based on momentum considerations, basically based on looking at the inertial to the viscous force. We can decide whether or not it's going to transition to becoming turbulent before or after it becomes fully developed as a laminar flow. And if it becomes turbulent before it becomes fully developed as a laminar flow, well, that means it's going to be a turbulent flow, right? Otherwise, it'll stay a laminar flow, and that doesn't change, right? It's the momentum considerations that dictate whether a flow is laminar or turbulent. But what is kind of interesting is to think about the fact that you can have a fluid that is for a little while laminar, right? Certainly in this entry length right here, if I find my pointer, you have basically a laminar flow, and as a result, you can have a fluid where the molecular Prandtl number is very different than 1. So you could have a fluid where it's developing from a momentum standpoint in a different way than it's developing from a thermal standpoint, right? So, for example, if we have a fluid with a Prandtl number greater than 1, we would expect this momentum boundary layer to be a lot bigger than the thermal boundary layer for as long as it's a laminar flow, right? But then for this particular flow, the critical position where it transitions to turbulence happens before it became fully developed, and therefore it transitions to a turbulent flow. And we said that because the turbulent viscosity is so large, we expect that once it transitions to turbulent flow, it will very quickly become fully developed, right? So let's think about what's going to happen thermally. Thermally, if I have a Prandtl number that's greater than 1, I would expect that the thermal boundary layer is going to sort of follow along here, but be a lot less than the laminar momentum boundary layer. But then as soon as it transitions to turbulence, what's going to happen? Well, the turbulent Prandtl number is always right around 1. No matter what the molecular Prandtl number is, the turbulent Prandtl number is going to be very close to 1, which is the same basically as saying that the turbulent that the turbulent thermal diffusivity, or the eddy diffusivity of heat transfer, is very similar to the turbulent kinematic viscosity, or the eddy diffusivity of momentum. And as a result, the turbulent boundary layers, the thermal and momentum turbulent boundary layers, they'll develop at about the same rate, right? Even though the laminar boundary layers were developing at very different rates because the molecular Prandtl number was very different than 1, the turbulent boundary layers, they're going to develop about at the same rate because the turbulent the Prandtl number is very close to 1. So that's a long-winded way of saying that as soon as it transitions to turbulent, even though the thermal boundary layers were growing slowly while it was laminar, as soon as it transitions to turbulent flow, that thermal boundary layer is going to grow just as quickly as the momentum boundary layer, right? So I would expect this to look something like this, right? I have this slow-growing laminar thermal boundary layer. It transitions to turbulence, and it becomes thermally developed almost as quickly as it becomes hydrodynamically developed, right? So as soon as it transitions to turbulence, you would expect it to become thermally fully developed very quickly, just like it becomes hydrodynamically developed very quickly. The heat transfer coefficient for a turbulent flow is made dimensionless using a Nusselt number, right? Same as what we've been talking about for external flows. We have two kinds of Nusselt numbers for internal flows. We have the local Nusselt number. We use that to normalize or to non-dimensionalize the local heat transfer coefficient. We also have the average Nusselt number, and we use that to non-dimensionalize the average heat transfer coefficient. And the average heat transfer coefficient here, just to be clear, that's the heat transfer coefficient over the entire duct length, right? The average of the heat transfer coefficient over the entire duct length. So if I'm sitting at some location right here, and I'm talking about the average heat transfer coefficient, what I'm talking about is the average heat transfer coefficient all the way from the inlet of the duct, averaged right up to where I'm sitting, right? That's what this average heat transfer coefficient is. So these are two different kinds of Nusselt numbers. Because we sort of understand how the local heat transfer coefficient behaves, right? We said that it's going to drop in the developing region and become constant in the fully developed region. We certainly know exactly how the local Nusselt number is going to behave, right? It's going to drop in the developing region and become constant in the fully developed region. The average Nusselt number behaves a little bit differently, and it does so because, again, the average Nusselt number, like the average heat transfer coefficient here, always remembers that there is this region at the beginning of the duct, this entry region, that had a high heat transfer coefficient. So, even though I might be out here where the heat transfer coefficient is, let's do it over here. I might be out here where the heat transfer coefficient is constant and equal to its fully developed value. The average heat transfer coefficient is integrated over the entire length of the duct. So it's going to be a little bit higher, and it's higher because it remembers this initial region. And so the average Nusselt number is always going to be a little bit higher than the local Nusselt number, right? As I move farther and farther down the duct, the impact of this is going to be less and less, but it's always going to be a little bit higher, and it just sort of approaches the local Nusselt number. All right, so what we'll do in the next lecture is talk about how these correlations behave, what the functional dependence of the correlations are, and then how you can actually access the correlations. And then following that, we'll do an example that uses these internal flow correlations.